On a clear night, away from city lights, you can see the Andromeda Galaxy with your bare eyes. A faint smudge of light, wider than the full moon, hangs quietly in the darkness. It looks close. It looks almost neighborly. It is 2.5 million light years away. If you launched a spacecraft today at the fastest speed any human object has ever traveled, it would not arrive before the sun burned out, before the Earth was swallowed, before every person alive today had been dead longer than our entire species has existed. And that is the nearest major galaxy. What lies between here and there is not empty space. It is a distance so vast it does not just prevent travel, it erases the meaning of the word. If this is the kind of science that pulls you in, hit like and subscribe. Now, let's begin. Go outside tonight. Find a place where the city lights do not reach. Drive out past the suburbs if you have to. Past the gas stations and the street lamps and the glow of parking lots that bleeds upward and paints the sky a dim orange. Find a field, a hilltop, a stretch of road where the ground is dark and the sky is honest. Then wait. It takes 15 to 20 minutes for your pupils to open wide enough to gather the faintest light, and most people never wait that long. They glance up, see a few bright stars, and go back inside. But if you wait, stars that were invisible a minute ago start appearing, first in ones and twos, then in clusters, then in rivers until the darkness between them seems full, in a way you did not expect. Now, look toward the constellation Andromeda. In the autumn sky of the northern hemisphere, it hangs high above the horizon. Find the great square of Pegasus first, then move your eye along a line of stars extending from its upper left corner. Partway along that line, slightly off to one side, you will see something that is not a star. Softer, slightly elongated. No blink, no twinkle. Just a faint smudge of light, quieter than everything around it. That smudge is the Andromeda Galaxy, not a cloud of gas within the Milky Way, not a cluster of nearby stars. It is an entirely separate galaxy, a vast rotating structure containing roughly 1 trillion stars, stretching more than 150,000 light years from edge to edge, held together by gravity and surrounded by a dark matter halo that extends even further. It is the nearest major spiral galaxy to our own. And on a clear dark night, you can see it with your bare eyes. The light reaching your retina tonight left Andromeda approximately 2.5 million years ago. When those photons began their journey, modern humans did not exist. Our ancestors were early members of the genus Homo, walking upright on the savannas of East Africa, working with crude stone tools. Every step of human history, every civilization, every war, every invention, every word of every language ever spoken has happened in the time it took that light to get here. It has been traveling at 300,000 kilometers per second without stopping, without slowing, without encountering anything substantial in its path for nearly the entire journey. And it only just arrived. This is where the illusion takes hold. Your brain looks at the night sky and processes everything it sees as a single scene. Stars, planets, the Milky Way's faint band, and that soft smudge near Andromeda's constellation all appear to sit on the same dark canvas. Your visual system does not distinguish between a star 10 light years away and a galaxy 2.5 million light years away. They are both points of light in the dark. They feel like they belong to the same neighborhood. They do not. And the distance between that feeling and reality is where this story begins. Every star you can see with your naked eye, every single one, is inside the Milky Way. They are your neighbors. Proxima Centauri, the nearest star to our sun, sits approximately 4.25 light years away. Sirius, the brightest star in the sky, is about 8.5 light years distant. The stars that form the constellations, the ones you learned as a child, the ones printed on charts and planetarium ceilings, range from a few dozen to a few hundred light years from Earth. Even the most distant naked eye stars are generally within 1,000 or 2,000 light years. In every case, these stars exist inside the same galactic structure you do. They share the same spiral arms, the same interstellar medium, the same slow rotation around the galactic center. They are part of your city. Andromeda is not in your city. Andromeda is not even on the same continent. Now here is the number that needs to settle in before anything else in this story will make sense. The nearest star is approximately 4 light years away. Andromeda is approximately 2.5 million light years away. That is not a modest increase. Andromeda is roughly 600,000 times farther than the closest star in the sky. 600,000 times. Interstellar travel, the crossing between stars within a galaxy, is already an almost impossible problem for human engineering. A spacecraft traveling at 1% of the speed of light, which is roughly 10 times faster than any object humanity has ever launched, would take approximately 425 years to reach Proxima Centauri. That is a journey spanning more than 5 human lifetimes. It would require propulsion systems that do not yet exist, life support technologies far beyond what has been tested, and either a crew willing to die before arrival or a way to keep human beings alive for centuries in a sealed metal container drifting between stars. It is a staggering challenge, but it sits within the range of what speculative engineering can at least sketch on paper. The numbers are enormous, but they are not absurd. Now multiply that travel time by 600,000. The same spacecraft, at 1% of the speed of light, would need approximately 250 million years to reach Andromeda. 250 million years. That number needs context because the human brain does not naturally process timescales that large. 250 million years ago, the dinosaurs had not appeared. The continents were joined into a single landmass called Pangaea. The largest mass extinction in Earth's history, the Permian extinction, was underway or about to begin, and it would wipe out roughly 90% of all marine species. The entire age of dinosaurs, their rise, their 160 million year reign, their catastrophic extinction, the subsequent rise of mammals, the evolution of primates, the emergence of humans, the invention of language, the development of agriculture, the construction of every city that has ever existed. All of that fits inside the travel time to the nearest major galaxy at a speed humanity cannot yet reach. Interstellar distance is a problem. Intergalactic distance is not a bigger version of that same problem. It is a different kind of problem entirely. One that does not merely make travel harder, but changes what the concept of travel means. To understand why that distinction matters, you need to see the structure of where we live. The Milky Way is a barred spiral galaxy approximately 100,000 light years in diameter. It contains somewhere between 100 billion and 400 billion stars. Our solar system sits about 26,000 light years from the galactic center, embedded in one of the galaxy's spiral arms, surrounded by stars in every direction. Within 10 light years of the Sun, there are roughly a dozen known star systems, Within 50 light years, several hundred. Within 500 light years, the number is in the tens of thousands. The galaxy is dense with stars, and that density matters in ways that are easy to overlook. Stars are not just destinations, they are infrastructure. Inside a galaxy, a star is a gravitational anchor that can be used for course corrections through flyby maneuvers. It is a potential energy source, either directly through its radiation or indirectly through the materials orbiting it. It is a navigation reference, a fixed point whose position can be measured and used to calculate location and heading. And it is, in many cases, surrounded by raw materials, asteroids, comets, moons, and planets that contain metals, water, and fuels that a spacecraft might theoretically use. The space between stars within the Milky Way is mostly empty by human standards. The interstellar medium has a density of roughly 1 atom per cubic centimeter, thin enough to qualify as a vacuum far beyond anything achievable in a laboratory on Earth. But the stars themselves are everywhere, separated by a few light years in dense regions, a few dozen light years in sparse ones. A civilization traveling between them would be moving from oasis to oasis across a desert that is vast but populated. Between galaxies, the oases disappear. The Milky Way is not alone. It belongs to a gravitationally bound collection of more than 50 galaxies called the Local Group, spread across roughly 10 million light years. But the phrase local group overstates the togetherness. The collection is dominated by 2 massive spirals, the Milky Way and Andromeda, with a third significant galaxy, the Triangulum Galaxy, known as M33, roughly 2.7 million light years from Earth. The rest are dwarfs, small galaxies with a few billion stars or fewer, scattered across the group like small towns spread thinly across a vast countryside. The closest galaxies to the Milky Way are satellite galaxies, gravitationally captured companions orbiting our galaxy the way moons orbit a planet. The Sagittarius Dwarf Elliptical Galaxy is only about 70,000 light years from Earth and is actively being torn apart by our galaxy's tidal forces, its stars being absorbed into the Milky Way's structure. The Large Magellanic Cloud sits roughly 160,000 light years away. The Small Magellanic Cloud is approximately 200,000 light years distant. Both Magellanic Clouds are visible from the southern hemisphere as conspicuous patches of light, bright enough that ancient navigators used them to orient themselves on open water. Even these nearby satellites are extraordinarily far by human standards. The Large Magellanic Cloud is about 40 times more distant than the far edge of the Milky Way's disk. Reaching it would require crossing not only the full breadth of our galaxy, but continuing outward into the halo beyond, through a region where stars thin to almost nothing, and then pressing on through tens of thousands of additional light years of increasingly empty space. And the Large Magellanic Cloud is still gravitationally connected to the Milky Way. Streams of hydrogen gas bridge the gap between us. It's a satellite, a suburb, still part of the same metropolitan area. But even these satellites, the closest galaxies to our own, are already beyond any interstellar reach that human engineering has ever contemplated. The Large Magellanic Cloud sits 160,000 light years from the Milky Way. The nearest star sits 4¼ light years away. That means the closest major satellite galaxy is roughly 38,000 times farther than the nearest star. If the journey to Proxima Centauri, a crossing of 4 light years would take approximately 425 years at 1% of the speed of light. Then a journey to the Large Magellanic Cloud at the same speed would take roughly 16 million years. And the Large Magellanic Cloud is not across the intergalactic void. It is orbiting inside the Milky Way's extended halo. It is, in galactic terms, right next to us. It is connected to our galaxy by streams of hydrogen gas that trail behind it like the wake of a boat. It shares our gravitational well. It sits well within the Milky Way's extended dark matter halo, which reaches roughly 300,000 light-years from the galactic center. And it is still 16 million years away at speeds that no spacecraft has come close to achieving. The Sagittarius Dwarf Elliptical Galaxy is even closer, roughly 70,000 light-years from Earth and approximately 50,000 light-years from the galactic center. It is so close that it is not merely orbiting the Milky Way. It is being consumed by it. Tidal forces from our galaxy's gravity are pulling the Sagittarius Dwarf apart, stretching it into long streams of stars that wrap around the Milky Way like threads being wound onto a spool. The galaxy is dying, not through collision in any explosive sense, but through a slow gravitational disassembly that has been underway for billions of years. And here is a detail that sharpens the point. The Sagittarius Dwarf is a galaxy, a gravitationally bound structure containing hundreds of millions of stars. It has survived for billions of years as a coherent system, and the mere act of passing through the Milky Way's halo at intergalactic proximity, close by galactic standards, is enough to destroy it. The tidal forces generated by the gravitational gradient between the outer halo and the inner disk are pulling it apart faster than its own gravity can hold it together. The crossing is killing it. Not rapidly, not violently, but absolutely. Given enough time, every star in the Sagittarius Dwarf will be absorbed into the Milky Way, and the galaxy will cease to exist as a distinct structure. A galaxy cannot survive the crossing intact. A bound system of hundreds of millions of stars, held together by its own gravity, is shredded by the tidal environment of the space between galaxies. The idea that a spacecraft, a single engineered object with no gravitational binding energy worth measuring, could survive a crossing that destroys galaxies is not merely ambitious. It is a claim made against the evidence of what that environment does to objects millions of times more massive and millions of times more structurally resilient. Andromeda is not a suburb. Andromeda is across an ocean with no islands, 2.5 million light-years of intergalactic void. The intergalactic medium is one of the most extreme environments in the known universe. Its density is roughly 1 atom per cubic meter, not per cubic centimeter as in the interstellar medium, but per cubic meter. That is roughly 1 million times emptier than the space between stars inside a galaxy. The Harvard-Smithsonian Center for Astrophysics describes it as emptier than the best vacuum achievable in any laboratory on Earth by a factor of billions. It is, by the standards of matter, almost nothing. But it is not cold. Paradoxically, the intergalactic medium is extraordinarily hot, with temperatures ranging from hundreds of thousands to tens of millions of degrees. This sounds lethal, and in a certain sense it is, but the gas is so sparse that a human body floating in it would not feel heat. There are simply too few particles per unit volume to transfer thermal energy at any meaningful rate. You would not burn. You would freeze, because the radiation of your own body heat into the vacuum would cool you far faster than the occasional collision with a stray atom could warm you. The temperature of the intergalactic medium is a measure of how fast its particles move, not how much energy they could deliver to a surface. It is hot in the physics sense and cold in the human sense. It is an environment defined by absence. No stars, no planets, no dust clouds dense enough to detect. No magnetic field strong enough to offer shielding from cosmic rays. No gravitational landmarks to navigate by. No fuel. No shelter. A spacecraft entering this void would leave behind the last faint stars of the Milky Way's outer halo and would not encounter another star until it reached the outermost edges of Andromeda's halo, millions of years later. And now, consider what humanity's most distant object has actually managed to do. Voyager 1 launched from Earth on September 5th, 1977. It flew past Jupiter in 1979. It flew past Saturn in 1980. After its Saturn encounter, it continued outward on a trajectory that has not been adjusted since. For nearly 50 years, it has been coasting through space at approximately 17 kilometers per second relative to the Sun, roughly 61,000 kilometers per hour. It crossed the heliopause in 2012, becoming the first human-made object to operate in interstellar space, beyond the protective bubble of charged particles generated by the Sun. In November of 2026, Voyager 1 will reach a milestone that puts the entire problem into focus. It will become the first human-made object to sit one full light day from Earth. One light day is the distance light travels in 24 hours, roughly 26 billion kilometers. From that distance, a radio command sent from mission control at the speed of light takes a full day to reach the spacecraft. A reply takes another day to return. A single exchange, one question and one answer, takes 48 hours. As of mid-2026, NASA lists only 2 science instruments still operating on Voyager 1. Its power supply, fueled by the slow radioactive decay of plutonium-238, loses roughly 4 watts of output every year. Engineers have been shutting down systems one by one to extend the mission's life, but the spacecraft is approaching the end of its functional existence. Within a few years, it will go silent. And here's what Voyager 1's position tells us about intergalactic distance. One light day is approximately 1/365th of a single light year. That sounds like a meaningful fraction until you remember that the nearest star is 4¼ light years away, more than 1,500 light days distant. To reach Proxima Centauri, Voyager 1 would need to travel roughly 75,000 years at its current speed. It has covered, in nearly 50 years, less than 1/1500th of the distance to the nearest star. Now extend that to Andromeda. At Voyager 1's speed, the journey to the nearest major galaxy would take approximately 45 billion years. The universe is 13.8 billion years old. Voyager 1 would need to fly for more than 3 times the current age of the entire universe just to cross the gap between here and the nearest galaxy that looks anything like our own. This is not a gap that better engineering closes. This is not a problem that a faster engine solves in the way that a faster car shortens a road trip. The distance between galaxies exists on a scale where the difference between current technology and even wildly optimistic future technology barely moves the needle. Even reaching the crossing speeds discussed earlier in this story, the journey to Andromeda stretches across timescales measured in tens of millions of years. The energy required to accelerate a spacecraft to even a fraction of that speed is already staggering. Even at 90% of the speed of light, accounting for relativistic effects that would compress the journey from the traveler's perspective, the home they left would age by more than 2.5 million years before they arrived. And this brings us to the last detail that makes the visible presence of Andromeda in our sky not beautiful, but quietly terrifying. Andromeda is moving toward us. The Milky Way and Andromeda are approaching each other at roughly 110 kilometers per second. For decades, scientists stated confidently that the two galaxies would merge in approximately 4.5 billion years. In 2025, a study published in Nature Astronomy using data from the Hubble and Gaia space telescopes ran 100,000 simulations and found the merger probability was only about 50% within 10 billion years. With the Large Magellanic Cloud's gravitational influence potentially deflecting the Milky Way from a direct collision course. Then, in March of 2026, a separate study from Peking University used updated Gaia proper motion data and 10,000 trajectory simulations to reach a different conclusion, finding a 90% merger probability with a median merger time of roughly 6.5 billion years. The science is actively debated. The data is still being refined. But for this story, the important point is not whether the merger will happen. It is how it will happen. If the Milky Way and Andromeda eventually combine, they will do so through gravity. Two structures falling toward each other across millions of light years over billions of years. No propulsion, no navigation, no crew, no purpose. Gravity does not need fuel. It does not need repair. It does not need to remember why the journey started. It has the one resource that no human mission will ever have: time without consequence. A spacecraft has to survive the crossing. A crew has to eat, breathe, and maintain their sanity. A mission has to preserve its purpose across a duration that exceeds every institution, every language, every political system, and every species that has ever existed on Earth. Gravity does not care about any of those things. It simply pulls, year after year, across epochs so vast that the word patience does not apply, because patience implies awareness of waiting. Nature can close the gap between galaxies. Whether anything human can do the same is a different question entirely. And the answer begins with what happens when you try to send a message across that void. Because when the distance is measured in millions of light years, communication does not just slow down, it stops being communication at all. Communication in space has always been a negotiation with the speed of light. Every conversation between a spacecraft and its home base involves a delay, a pause enforced by physics that no technology can shorten. Light moves at roughly 300,000 kilometers per second. Nothing moves faster. Every command, every data packet, every image captured by a camera on a distant world must travel at that speed or slower. We can make signals stronger, receivers more sensitive, encoding more efficient. But we cannot make information arrive faster than physics permits. On Earth, this delay is invisible. A signal crosses the planet in roughly 1/10 of a second. But move the conversation into space, and the delay begins to assert itself. When NASA communicates with the International Space Station, the delay is negligible, less than a second. The station orbits roughly 400 kilometers above the surface. Controllers can speak to astronauts in something resembling real-time conversation, watch live video, and respond to emergencies within seconds. The station feels close because, by cosmic standards, it is close. It sits within the thin envelope of near-Earth space, still wrapped in the planet's magnetic field, still visible to the naked eye from a dark backyard if you know when to look. Move the conversation to the moon, and the delay becomes noticeable. The moon orbits approximately 384,000 kilometers from Earth. A signal takes roughly 1.25 seconds to reach it. That means every exchange carries a 2.5-second round trip. During the Apollo missions, this gap showed up in the voice transmissions. Listen to the recordings carefully and you can hear it. A faint but consistent hesitation between a question from Houston and the response from the lunar surface. It was manageable. Controllers could still react to problems within seconds. A genuine emergency could be addressed before it escalated beyond recovery. The delay was present, but it did not break the operational relationship between the crew and the people supporting them. Move the conversation to Mars, and the relationship starts to strain. Mars orbits between roughly 55 million and 400 million kilometers from Earth, depending on where both planets sit in their orbits. At its closest approach, a signal takes approximately 3 minutes to travel one way. At its most distant, the delay stretches to over 22 minutes. A round trip at the farthest point means that if a rover on the Martian surface sends an image to Earth and Mission Control immediately sends a response, the rover will not receive the reply for nearly 45 minutes. This is why Mars rovers do not operate the way remote-controlled cars do. Engineers on Earth cannot drive them in real time. Instead, they upload a package of commands each morning that tells the rover what to do for the day. The rover executes those instructions autonomously, records the results, and sends the data back. Controllers review the results and write a new set of instructions for the following day. It works, but it is not a conversation. It is a slow correspondence, a system of letters sent back and forth across a gap that makes spontaneous decision-making impossible. Now consider what this delay means for human missions. If astronauts on Mars face a sudden emergency, a medical crisis, a structural failure, a dust storm threatening the habitat, they cannot call home and get an answer in time to act on it. The delay is long enough that the situation will have evolved, worsened, or resolved itself before any guidance from Earth arrives. Astronauts on Mars must be capable of independent decision-making at a level no space crew has ever been required to sustain, because for significant stretches of their mission, they are effectively on their own. Mission Control becomes an advisor rather than a commander. It can offer analysis after the fact. It cannot intervene in the moment. This is the communication reality at the scale of a single solar system. And this is the scale at which human space operations currently function, just barely, with significant difficulty, supported by decades of institutional knowledge and billions of dollars of ground infrastructure. But before we make that jump, it is worth walking through the middle distances, the ones between Mars and the stars, because they reveal how the delay grows from frustrating to disabling in stages that are easy to skip over when the numbers get large. Move the conversation past Mars, out to Jupiter. At its average distance from Earth, a signal takes roughly 43 minutes to travel one way. A round trip is nearly an hour and a half. The Juno spacecraft, orbiting Jupiter since 2016, operates on a command cycle measured in hours. It executes preloaded sequences, records data, and transmits it back in scheduled windows. The relationship between the spacecraft and its ground team is no longer a conversation. It resembles a series of memos exchanged between officers in different time zones, except the time zones are separated by the width of the solar system. Push further to Saturn. The Cassini mission operated at Saturn for 13 years, at a distance where one-way light time ranged from roughly 71 minutes to 87 minutes, depending on orbital geometry. A round trip approached nearly 3 hours at maximum distance. Now, by that point, mission controllers could not react to any event on the spacecraft within the same work shift during which it occurred. A problem detected in data received at 9 in the morning could not receive a corrective command that arrived at Saturn before the afternoon, and the spacecraft would not confirm receipt until evening. An entire working day consumed by a single exchange. The operational rhythm was not conversation, not correspondence, but something closer to issuing orders into a void and waiting to learn whether they were followed. Now move to the edge of the solar system, the Kuiper Belt, the band of icy bodies beyond Neptune's orbit, begins roughly 30 astronomical units from the Sun and extends to approximately 50. 1 astronomical unit is the distance from the Earth to the Sun, roughly 150 million kilometers. At 50 astronomical units, a signal takes about 6 hours and 55 minutes to travel one way. A single round-trip exchange takes nearly 14 hours. When the New Horizons spacecraft flew past Pluto in 2015, at a distance of roughly 33 astronomical units, the one-way light time was about 4.5 hours. Every image of Pluto's surface that thrilled the world had been captured hours before anyone on Earth knew it existed. Every course correction sent from Mission Control was based on information that was already half a day old by the time the command arrived. Beyond the Kuiper Belt lies the Oort cloud, the hypothetical shell of icy bodies that marks the gravitational boundary of the Sun's influence. Its inner edge is estimated at roughly 2,000 astronomical units. Its outer edge may extend to 100,000 astronomical units, or approximately 1.5 light years. A signal sent to a spacecraft at the inner edge of the Oort cloud would take about 11.5 days to arrive. At the outer edge, it would take over 18 months one way. A 3-year round trip for a single exchange. At that distance, the communication is no longer operational in any recognizable sense. It is a slow pulse between two entities that share a solar system in name, but not in practice. And all of that, every escalating delay from Jupiter to Saturn to the Kuiper Belt to the Oort cloud, it is still inside the Sun's gravitational domain. It is still interplanetary. It has not yet become interstellar. The nearest star remains nearly 3 times further than the outer Oort cloud. The delay does not grow in a straight line. It grows in a curve that steepens as you move outward, each step adding not just more distance, but a qualitative change in the relationship between the traveler and the ground. At Jupiter, the conversation is sluggish. At Saturn, it is a series of scheduled dispatches. At the Kuiper Belt, it is a daily correspondence. At the Oort cloud, it is a seasonal exchange. At the nearest star, it is a generational project. And at the nearest major galaxy, it is geological. Each transition along that curve strips away a layer of operational capability. First, you lose real-time control. Then you lose same-day response. Then you lose same-month dialogue. Then you lose the ability to hold a conversation within a single human career. And finally, you lose the ability to hold a conversation within the lifespan of the civilization conducting it. Now stretch the distance to the nearest star. Proxima Centauri sits approximately 4.25 light years from Earth. A signal sent to a spacecraft orbiting that star would take 4 years and 3 months to arrive. A reply would take the same amount of time to return. One complete exchange, a single question, and a single answer would take 8.5 years. Picture what that means operationally. A crew in the Proxima Centauri system encounters a problem. The ship's primary oxygen recycler fails. They have a backup, but the backup requires a software patch that was not included in the original mission package. They transmit a request to Earth, describing the failure in detail and asking for the patch. The signal travels at the speed of light for 4 years and 3 months. It arrives at the Deep Space Network receiver on Earth. Engineers analyze the problem, write the patch, test it, verify it, and transmit it back. The response leaves Earth and travels for another 4 years and 3 months. 8.5 years have passed since the crew reported the problem. In that time, the crew has either solved the issue on their own, devised a workaround, or died. The answer from Earth, when it arrives, is a historical document. It describes a solution to a problem that was resolved or became fatal nearly a decade earlier. This is not communication in any operational sense. It is correspondence between two groups of people who are living in different periods of relevance. And yet, interstellar communication, as impractical as it is, still preserves something recognizably human. The crew that sends a message and the engineers who receive it could plausibly be alive at the same time. A signal crossing 4 light years arrives within a single human lifetime. The people on both ends might age, but they would still exist. They could still share a language. They could still reference the same institutions, the same history, the same cultural framework. The conversation is absurdly slow, but it is a conversation between contemporaries. Intergalactic communication destroys even that. A signal sent from Earth toward the Andromeda Galaxy, traveling at the speed of light, would take approximately 2.5 million years to arrive. This is not a delay that slows communication. It is a delay that abolishes it. You already know what 2.5 million years means. We measured it earlier by the age of the light arriving from Andromeda tonight. But knowing the timescale and feeling its operational consequence are different things. Every language spoken on Earth today will be extinct long before that signal arrives. Every nation that exists now will have risen and fallen and been forgotten. Every scientific framework, every data format, every unit of measurement currently in use will have been replaced so many times that the replacements themselves will be ancient history. The entire accumulation of human thought, from the first cave painting to this sentence, fits inside the travel time of a single signal to Andromeda. A message sent from Earth today would arrive at Andromeda in a future so remote that nothing about the present would remain recognizable. Whatever civilization existed on Earth when the signal departed would be as distant from the receivers as the Australopithecines are from us. If anyone or anything at the destination were listening and chose to reply, the reply would take another 2.5 million years to return. The total round trip is 5 million years. 5 million years. The species that sent the message would almost certainly not exist when the answer came back. The language would be gone. The culture would be gone. The political structures would be gone. The biological form of the senders would likely have changed through evolution, genetic engineering, or extinction. The reply would arrive on a planet populated by beings who share no meaningful connection to the ones who asked the question, and it would reference a question that no living memory, no archive, and quite possibly no surviving civilization could contextualize. This is not a communication delay. This is a gap between geological epochs. A message crossing this distance is not a letter. It is a fossil. Now, consider what this means for the operating concepts that every space mission in history has depended on. Every mission humanity has ever flown has relied on a basic structural assumption. The mission has a command authority. There is a room, or a building, or a network of facilities, staffed by people who monitor the spacecraft, analyze data, send corrections, and make decisions when things go wrong. The crew is never truly alone because even when the delay is frustrating, mission control is there. It has access to engineers, doctors, computer systems, databases, and institutional memory that the crew cannot carry with them. The relationship between the crew and the ground is the backbone of every space operation ever conducted. At intergalactic distances, mission control does not exist. It is not that the building closes or the staff is laid off. It is that the concept of a command authority separated from the crew by millions of light years is operationally meaningless. A command authority that cannot receive information about a problem until millions of years after it occurs, and cannot deliver guidance until millions of years after the information arrives, is not part of the mission. It is a memory, an artifact from the era when the mission began. It has no more operational relevance to the crew than a letter written by a Roman senator has to a person living today. A crew crossing intergalactic space is not just far from home, they are severed from it. The severance is not emotional or metaphorical. It is physical, enforced by the speed of light, absolute and permanent from the moment the spacecraft leaves the galaxy's outermost halo. No technology can fix this because the problem is not technological, it is geometric. The distance is too large for information to be relevant by the time it crosses the gap. And if communication collapses, every system that depends on communication collapses with it. Rescue is the most visceral example. In the history of human spaceflight, rescue has always been at least theoretically possible. When Apollo 13 suffered an oxygen tank explosion on the way to the moon, Mission Control worked around the clock to devise solutions using only the materials aboard the spacecraft. The crew swung around the moon and returned to Earth. The delay was a second and a quarter each way. The situation was resolved in days. When the Space Shuttle Columbia broke apart during re-entry in 2003, the loss was catastrophic and unrecoverable, but the failure occurred within direct contact range of the ground. The decision-making loop between the crew and the people who could potentially help them was measured in seconds, not years. At interstellar distances, rescue becomes a theoretical exercise. A ship in distress near Proxima Centauri could send a signal, but help, if it could be sent at all, would not arrive for decades at minimum. The crew would have to survive whatever went wrong for longer than most of them would live, using only what they carried. At intergalactic distances, the word rescue does not apply. A ship in distress between the Milky Way and Andromeda could transmit a distress signal, and that signal would travel outward at the speed of light. If the ship were 1 million light years from the Milky Way, the signal would reach Earth in 1 million years. If Earth still had the capability to detect it, and if the civilization that received it decided to respond, and if they could somehow launch a rescue vessel fast enough to matter, that vessel would still take hundreds of thousands of years at best to reach the location where the distress call originated. By that time, the crew would not just be dead. They would have been dead so long that their bones would have turned to dust, The dust would have dispersed into the intergalactic medium, and the atoms that once formed their bodies would be scattered across a volume of space, large enough to be invisible to any instrument. Rescue at intergalactic distances is not slow, it is meaningless. The gap between the moment a problem occurs and the earliest possible moment help could arrive is so vast that the concept of help no longer functions. Resupply collapses along the same timeline, and in some ways it collapses even harder because resupply involves the movement of physical matter, not just information, and matter travels far slower than light. Every space mission in history has depended on a supply chain. The International Space Station receives cargo ships multiple times per year, delivering food, water, spare parts, replacement hardware, experimental equipment, clothing, and medical supplies. Without those deliveries, the station would become uninhabitable within months. The crew consumes resources faster than onboard systems can fully recycle them, and critical components wear out on schedules that require physical replacement. Even missions that carry everything they need at launch depend on a conceptual supply chain. The Apollo missions carried all their consumables, but they were designed for round trips of less than 2 weeks. The supplies were calculated against a known timeline with narrow margins. If a system failed that could not be repaired with onboard materials, the mission was aborted and the crew returned home. The supply chain was compressed into the vehicle itself, and the vehicle was never more than a few days from the depot. A crewed interstellar mission would need to carry not just consumables, but the means to produce consumables indefinitely. Closed-loop life support systems that recycle water and air, agricultural modules that grow food, manufacturing capabilities that can fabricate replacement parts from raw materials, medical facilities that can treat injuries and illnesses without resupply of pharmaceuticals. The ship must become a self-sustaining world, carrying not just provisions, but the entire industrial and biological infrastructure needed to regenerate them. This is extraordinarily difficult even in theory. No closed-loop system ever tested has achieved perfect recycling efficiency. Losses accumulate, trace contaminants build up. Biological systems require inputs that cannot be synthesized from available materials. Over decades, these imperfections compound into shortfalls. Over centuries, they compound into crises. Over millions of years, even a system operating at 99.9% efficiency will have accumulated losses so large that the original resource base is exhausted many times over. At interstellar distances, resupply from home is at least theoretically possible, if painfully slow. A cargo package launched from Earth toward a colony at Proxima Centauri would take decades or centuries to arrive, depending on its speed, but it would eventually get there. A pipeline of supplies launched at regular intervals could in principle sustain a distant outpost, the way supply ships sustain a remote research station in Antarctica. The logistics would be brutal but conceivable. At intergalactic distances, resupply from home is not slow. It is non-existent. A cargo package launched from the Milky Way toward a ship crossing the void to Andromeda would need to travel the same millions of light years, taking the same millions of years. And by the time it arrived, the ship would have moved millions of additional light years along its trajectory, requiring course corrections that could not be transmitted in time to matter. The supply chain does not stretch across intergalactic distance. It snaps, completely permanently, at the moment of departure. A crew crossing the intergalactic void carries everything it will ever have. there is no depot behind them. There is no delivery coming. Every atom of matter aboard the ship at departure is the total inventory for a journey lasting millions of years. If a critical component breaks and cannot be fabricated from available materials, it stays broken. If a nutrient becomes depleted that the biological systems cannot synthesize, it stays depleted. If a tool is lost, a chemical is contaminated, a seed bank fails, a water reservoir cracks, and there is no warehouse to call and no delivery window to wait for. The ship does not run out of supply. It runs out of options, and options, once exhausted, do not regenerate across a void where nothing else exists. Return follows the same logic. Every mission in human history, whether it was a 3-day trip to the moon or a theoretical multi-decade voyage to another star, has carried within it an implicit promise: you can come back. The journey has a beginning and an end. The end is home. Even in the most extreme interstellar mission concepts, the idea of return is present, at least as a theoretical possibility. A generation ship might not bring back the people who departed, but their descendants could choose to reverse course. A robotic probe can be programmed to transmit its data back to Earth. The connection to home, however thin, is maintained. At intergalactic distances, return is not difficult, it is incoherent. A crew that somehow crossed the void to Andromeda, and then immediately turned around to come home, would spend a minimum of 5 million years in transit at the speed of light. At any achievable fraction of light speed, the round trip would take tens of millions to hundreds of millions of years. The Earth they left would not exist in any form they would recognize. The continents would have shifted. The climate would have changed. The species living on the surface would be different. The sun itself, while still burning, would be measurably further along in its main sequence lifetime. The concept of home requires continuity. It requires that the place you're going back to has something in common with the place you left. At intergalactic timescales, continuity is the first casualty. The home is gone, not destroyed, not conquered, not abandoned, simply changed beyond recognition by the ordinary passage of time. And this leads to perhaps the most quietly devastating implication of intergalactic distance. Not just that you cannot be rescued, not just that you cannot return, but that the reason for the mission may not survive the crossing. Every journey requires a purpose. Someone has to decide to go, and they have to have a reason for deciding. That reason exists within a context. A civilization, a government, a scientific institution, a cultural moment. The decision to launch a mission to Andromeda would be made by people embedded in a specific time and place, with specific goals, specific questions they wanted answered, specific values that made the effort seem worthwhile. But even the most optimistic crossing time to Andromeda, the 25 million year figure established earlier, dwarfs the frame within which human institutions operate. The civilization that launched it would have to sustain its purpose, its funding, its institutional memory, and its interest in the mission's outcome for a duration that exceeds the entire existence of the genus Homo by a factor of more than 10. No institution in human history has lasted more than a few thousand years. Most last a few centuries. The idea that a mission purpose could survive across 25 million years of political change, cultural evolution, a technological revolution, and potential civilizational collapse is not optimistic. It is fictional. A generation ship crew, thousands or millions of years into an intergalactic crossing, would have no living connection to the civilization that built their vessel. The language would have evolved beyond recognition. The mission objectives, whatever they originally were, would be historical texts from an era so remote that even the concept of era would have lost its meaning. The crew's understanding of who they are, where they came from, and why they're traveling would be filtered through hundreds of thousands of generations of retelling, reinterpretation, and forgetting. The mission that began with a question asked by a living civilization would continue long after the civilization that asked it could no longer hear the answer. The question would still be traveling outward. The answer would still be forming, but the relationship between the two would have been severed by distance so completely that neither side would recognize the other. And Mission Control, back on Earth, would face the mirror image of this problem. Even if the institution somehow survived, even if the receivers still listened for the signal, the data that eventually arrived from the spacecraft would reference questions nobody remembered asking. Observations calibrated to instruments nobody remembered building, and discoveries framed in terms that nobody could interpret, because the scientific paradigms of the launching era would be as distant as alchemy is to modern chemistry. The data would arrive. It would be real. It would represent genuine observations of another galaxy. And it would be received the way archaeologists receive inscriptions on clay tablets from civilizations that no longer exist. Not as a message, as an artifact. And even calling it an artifact may be generous, because an artifact implies that someone on the receiving end can study it, interpret it, and extract a meaning from it. Across intergalactic timescales, even that assumption fails. Language is not permanent. Every language ever spoken on Earth has changed, fragmented, or died within a few thousand years at most. Old English, spoken roughly 1,000 years ago, is unintelligible to a modern English speaker without specialized training. Latin, spoken 2,000 years ago, survives only in modified descendant languages and in academic study. Languages from 5,000 years ago are accessible only through painstaking reconstruction from fragmentary inscriptions. Beyond that, the record disappears. We have no knowledge of any language spoken more than roughly 6,000 years ago, and the ones we do have are known only because they were carved into materials durable enough to survive. A signal arriving from a spacecraft after 2.5 million years of travel would carry information encoded in the language, conventions, data formats, and conceptual frameworks of the civilization that launched it. Every aspect of that encoding would be opaque to the receivers. The language would bear no resemblance to whatever communication system the receiving civilization used. The data formats, the compression algorithms, the error correction protocols, the metadata structures, all of it would be as foreign as cuneiform is to a child who has never seen writing. But the problem runs deeper than translation. Even if the receiving civilization could somehow decode the language and read the data, the information itself would reference concepts, categories, and assumptions that no longer existed. Scientific measurements calibrated to instruments whose specifications were lost. Observations framed within theoretical models that had been superseded thousands of times over. Questions that had been answered, reformulated, or abandoned so long ago that the intellectual tradition connecting them to the present had evaporated without a trace. Consider what would happen if a message arrived on Earth today from a civilization that had sent it 2.5 million years ago. Not from another galaxy, but from our own planet, hypothetically. transmitted by a species of early hominid that somehow possessed radio technology. The message would be in a language no human has ever heard. It would reference a world that no longer exists. It would describe flora and fauna that are extinct. It would measure time, distance, and quantity using systems that have no correspondence to anything in modern use. It would ask questions that no living mind could contextualize and report observations that no living discipline could evaluate. We would know it was a message. We would know it carried meaning. And we would have no way to recover that meaning in its original form. We could study the signal as an object, analyze its structure, note its regularities, hypothesize about its content. But the conversation it was meant to be part of ended before our species was born. That is what waits on the receiving end of an intergalactic transmission. Not silence, something worse. A voice, perfectly preserved, speaking words no one alive can understand, answering a question no one alive remembers asking, reporting from a world no one alive has ever seen. The signal crosses the void intact. The meaning does not. This is the specific sense in which intergalactic distance transforms communication into archaeology. The information crosses the void intact. Light does not forget. A signal does not decay because of the distance alone, though it weakens with the square of the distance and would require extraordinary receiver sensitivity to detect after millions of light years. But the meaning of the information, its relevance, its connection to a living question asked by a living mind, that does not survive the crossing. Meaning requires context. Context requires continuity, and continuity cannot stretch across millions of years without snapping. Inside a galaxy, communication is slow but functional. A signal to Proxima Centauri arrives within a lifetime. The sender and receiver can share a language, a culture, a frame reference. The delay is painful but survivable. Communication across interstellar space is like shouting across a wide canyon. The words arrive late and faint, but they arrive to someone who can understand them. Between galaxies, communication is something else. The words arrive, but the canyon has become so wide that by the time the shout reaches the other side, the person who shouted has been dead for millennia. Their language is extinct. The civilization they belong to is a layer of sediment in a geological record that may or may not still be accessible. The shout is preserved perfectly in the signal, but the signal lands on a shore where no one knows what it means. And this is the gap between interstellar travel and intergalactic travel that most discussions fail to make clear. Interstellar distance makes travel extremely hard. It makes communication painfully slow. It strains every system we depend on. But it does not fundamentally break the relationship between the travelers and their home. A crew at Proxima Centauri could, in theory, maintain a correspondence with Earth. It would be glacially slow. It would take years per exchange. But it would be real. Both parties would be alive. Both would share enough common ground to understand each other. The mission would remain connected to its origin, however tenuously. Intergalactic distance breaks the relationship. It does not strain it. It does not stretch it thin. It severs it, permanently, irreversibly, the moment the spacecraft leaves the gravitational neighborhood of its home galaxy. From that moment on, the crew is not just far from home. They are in a different era from home. They exist in a different chapter of their homeworld's history, a chapter that has not been written yet and will not be written for millions of years. There is a phrase used in mission planning that captures the relationship between a crew and their ground support. It is called the communication link. Everything depends on it. Telemetry flows through it. Commands flow through it. Medical data, navigation corrections, software updates, morale messages, news from home, all of it travels along the communication link. When the link is strong, the mission is connected. When it degrades, the mission becomes vulnerable. When it fails, the crew is on their own. At intergalactic distances, the communication link does not fail. It does something worse. It continues to function, technically, transmitting signals that travel dutifully at the speed of light through the void. Signals that carry real data, real observations, real words spoken by real people. But the signals arrive so far in the future that they serve no operational purpose. The link exists. The information flows, and none of it matters because the people on both ends are separated not by distance alone, but by time so deep it buries everything. The danger of intergalactic distance is not that it blocks communication. It is that it renders communication ceremonial. The signals still travel. The messages are still sent. But they arrive as monuments rather than conversations. Testaments to the fact that someone once existed and once tried to speak across a void so vast that the universe itself could age while the words were in transit. And that realization leads directly to the next question. If communication is meaningless, and rescue is impossible, and return is incoherent, and mission control is an archaeological memory, then what happens to the crew, the probe, or the vessel itself during the crossing? What does it mean to physically survive in the intergalactic void for millions of years? The answer is that survival at this scale is not a human problem. It is an engineering problem so extreme that it stops resembling engineering and starts resembling geology. There is a difference between a journey that is long and a journey that outlasts the machine making it. Every spacecraft humanity has ever built was designed for a lifespan measured in years. A few were designed for decades. None was designed for centuries. And nothing in the history of engineering, nothing ever manufactured by human hands and launched into space, offers any precedent for a vehicle that must function for millions of years. This is the survival problem of intergalactic travel. Not whether a spacecraft can point itself toward Andromeda and start moving. That part is conceptually straightforward. The problem is whether any physical object, any combination of material circuits, fuel reserves, moving parts, and structural components can hold itself together for the duration of the crossing. And the answer, measured against everything we know about materials, science, thermodynamics, and the behavior of matter over extreme timescales, is almost certainly no. Start with power. Every spacecraft requires energy. Energy runs the computers that process navigation data. It runs the communication systems that transmit signals. It runs the heaters that keep instruments within their operating temperature range. It powers the attitude control systems that keep the spacecraft oriented correctly. Without power, a spacecraft is not a vehicle. It is debris. The most durable power systems ever flown in space are radioisotope thermoelectric generators. These devices convert the heat produced by the natural decay of a radioactive isotope, typically plutonium-238, into electrical current. They have no moving parts. They do not require sunlight. They function in any orientation, at any distance from a star, in any environment. They are the reason Voyager 1 is still transmitting after nearly 50 years, the reason Cassini could sustain its long mission at Saturn without sunlight, and the reason the New Horizons spacecraft was able to study Pluto and then continue into the outer solar system. But radioisotope thermoelectric generators have a fixed lifespan determined by the half-life of their fuel. Plutonium-238 has a half-life of approximately 87.7 years. That means that every 87 years, the fuel produces half as much thermal energy as it did at the start of that period. Voyager 1's generators produced roughly 470 watts at launch in 1977. By 2026, they produce approximately 220 watts, and that number drops by roughly 4 watts every year. Within the next few years, the power output will drop below the threshold needed to operate even a single instrument, and the spacecraft will fall silent. 87 years of useful power from the most durable energy source humanity has ever flown. The crossing to Andromeda at 10% of the speed of light takes 25 million years. The ratio between those two numbers is not a gap that incremental improvement can bridge. You cannot simply carry more plutonium. The mass of fuel required to sustain power output for millions of years would be so enormous that the spacecraft could not carry it. And even if it could, the containment vessel holding the radioactive material would itself degrade over those timescales, raising problems of structural integrity that loop back into the same fundamental issue. Solar power is irrelevant between galaxies. There is no star to collect energy from. The nearest star is millions of light years behind you or millions of light years ahead. The ambient light in the intergalactic void, a faint wash of red-shifted photons from distant galaxies, and the cosmic microwave background carries so little energy per unit area that a solar panel the size of a continent would struggle to power a single light bulb. Nuclear fission reactors have been tested in space, but they require coolant systems, control mechanisms, and fuel that is consumed over time. Their lifespans, even in the most optimistic designs, are measured in decades. Fusion power, if it is ever achieved in a compact enough form to mount on a spacecraft, would still require fuel, containment, and maintenance over timescales that dwarf any engineering warranty ever written. The power problem is not unsolved. It is, in the context of intergalactic travel, unsolvable with any known or projected technology. The timescale of the journey exceeds the operational lifetime of every energy system humanity has conceived by a factor of at least tens of thousands. Now consider propulsion. To reach 10% of the speed of light, a spacecraft must accelerate to approximately 30,000 kilometers per second. For reference, the fastest human-made object ever launched is the Parker Solar Probe, which reached speeds exceeding 160 kilometers per second relative to the Sun during its closest solar approaches. Voyager 1, by comparison, travels at 17 kilometers per second. The gap between even the Parker Solar Probe's record-breaking speed and 10% of light speed is still a factor of roughly 180. And the gap from Voyager 1's cruising speed is a factor of roughly 1700. Closing that gap requires energy on a scale that dwarfs anything in the history of human engineering. A spacecraft with a mass of 1,000 metric tons, modest by the standards of any vehicle that could support human life for extended periods, would require kinetic energy equivalent to roughly 400 billion joules to reach 10% of light speed. That is comparable to the total energy consumed by every nation on Earth across an entire year, concentrated into accelerating a single object. The propulsion system capable of delivering that energy does not exist. Chemical rockets, the workhorses of every space mission to date, are nowhere near sufficient. Their exhaust velocities are too low by orders of magnitude. Ion drives, which achieve much higher exhaust velocities, produce thrust so small that accelerating a crewed vessel would take centuries even in the best theoretical configurations. More exotic concepts have been proposed. Nuclear pulse propulsion, in which a spacecraft detonates nuclear devices behind itself and rides the shockwave forward, was studied under Project Orion in the 1960s. It could theoretically achieve a few percent of light speed, but the engineering challenges are extreme and the political obstacles to launching thousands of nuclear weapons into space are formidable. Antimatter propulsion offers the highest theoretical energy density of any fuel, but humanity currently produces antimatter in quantities measured in nanograms per year, and containing it requires magnetic fields sustained at enormous energy costs. Beamed propulsion, in which a powerful laser or microwave array on the home end pushes a sail-equipped spacecraft, could accelerate small probes to significant fractions of light speed. But the beam weakens with distance, and the system only works for acceleration away from home. It offers no way to slow down at the destination. Each of these systems, even the most optimistic ones, was designed for interstellar distances. They were conceived to cross gaps of 4 to 40 light years, with travel times of decades to centuries. Scaling any of them to intergalactic distances does not just increase the engineering difficulty. It transforms the problem into something qualitatively different, because the journey time exceeds the lifespan of the propulsion system itself. The structural materials of the spacecraft, the electronic components, and every other physical element of the vehicle. This is where the concept of survival stops resembling a human problem and starts resembling a geological one. The question is no longer how to keep a crew alive. It is whether the atoms that make up the spacecraft will still be arranged in a functional configuration after millions of years in the void. Materials degrade. This is not a dramatic failure. It is a slow, relentless, universal process that applies to every physical object in the universe. Metals corrode, even in vacuum, through sublimation, where individual atoms escape the surface at a rate determined by temperature and material properties. The rate is extremely slow, but over millions of years, even slow processes accumulate into significant effects. Micrometeorite impacts, even in the sparse intergalactic medium, would sandblast exposed surfaces across timescales that long. Cosmic rays, high-energy particles traveling at nearly the speed of light, penetrate the hull and interact with the materials they pass through, displacing atoms in crystal lattices, creating defects that accumulate and weaken structural components. Radiation damage to electronics is a well-documented problem on timescales of years. Over millions of years, it would be catastrophic. Every integrated circuit, every solder joint, every semiconductor junction would be progressively destroyed by this cumulative impact of high-energy particles. And materials degradation is only the passive side of the problem. There is an active side that is equally devastating: repair. Every complex machine ever built requires maintenance. This is not a design flaw. It is a consequence of the second law of thermodynamics. Ordered systems tend toward disorder. Moving parts wear against each other. Seals degrade. Lubricants oxidize, evaporate, or break down under radiation exposure. Fasteners loosen under thermal cycling as components expand and contract through temperature changes. Welds develop microfractures, bearings lose tolerance, valves stick, filters clog, wiring insulation becomes brittle and cracks, exposing conductors to short circuits. On Earth, we manage this through an infrastructure of maintenance that is so pervasive it becomes invisible. Cars are serviced every few months. Aircraft are inspected after every flight and undergo major overhauls on fixed schedules. Power plants employ full-time maintenance crews who replace components continuously. Even the International Space Station, the most self-contained crewed structure ever built, requires constant maintenance by its crew, supplemented by replacement parts delivered from Earth on a regular schedule. Astronauts aboard the station spend a significant fraction of their working time on repair and upkeep, fixing equipment that has worn, broken, or degraded since the last maintenance cycle. A spacecraft crossing intergalactic space cannot receive replacement parts. It must carry everything it will ever need for maintenance, or it must manufacture replacements from raw materials aboard the vessel. The first option is limited by mass and storage volume. You cannot carry enough spare parts to sustain a vehicle for millions of years, because the number of parts that could potentially fail over that timescale is essentially the total number of parts in the vehicle. The second option requires an onboard manufacturing capability sophisticated enough to fabricate any component the spacecraft uses, from microchips to structural beams to pressure seals, using only the materials available within the ship's closed inventory. Building such a manufacturing system is an extraordinary challenge. It would need machine tools that can themselves be maintained and repaired using other machine tools, creating a recursive loop of self-sustaining fabrication. At some level, this chain must bottom out at processes simple and robust enough to be performed with minimal infrastructure. Casting, forging, machining from raw metal stock. But even those processes require consumables, cutting fluids, abrasives, energy, and feedstock, all replenishable only from the ship's finite inventory. Over thousands of years, this closed manufacturing loop might function. Over millions of years, it faces the same entropy problem as every other system aboard. The machine tools wear. Their precision degrades. Parts fabricated by degraded tools are less precise than the originals. And those less precise parts are used to maintain other systems, propagating the degradation forward. Each generation of replacement components is slightly worse than the last, a slow ratchet of declining quality that eventually drops below the threshold of functionality. This is the maintenance death spiral, and it applies to every mechanical system operating on intergalactic timescales. Not a sudden failure, but a gradual, compounding erosion of capability. The ship does not break, it blurs. Its systems do not stop. They become imprecise, and imprecision accumulated across millions of years of self-repair with degrading tools and diminishing feedstock eventually produces a vehicle that still exists as a structure but no longer functions as a machine. A civilization far more advanced than ours might engineer materials and systems of extraordinary durability, reducing the maintenance burden significantly. But reducing is not eliminating. No physical system is maintenance-free forever. The question is only how long it can defer the inevitable, and against a crossing measured in millions of years, deferral is not a solution. It is a slower path to the same outcome. Inside a galaxy, cosmic rays are a manageable hazard. The galaxy's magnetic field provides a degree of diffuse shielding, bending the paths of lower energy particles and reducing the flux that reaches any given point. Spacecraft designers account for cosmic ray exposure and build intolerances. Between galaxies, that magnetic shielding largely disappears. The intergalactic medium carries extremely weak magnetic fields, estimated at roughly 1/1000th of a Gauss in the voids between galaxy clusters, roughly 1,000 times weaker than the galactic magnetic field, and far too feeble to deflect incoming high-energy particles in any meaningful way. A spacecraft in the intergalactic void is exposed to the full unshielded flux of extragalactic cosmic rays, including ultra-high energy particles from sources across the observable universe. Shielding against cosmic rays is one of the most stubborn, unsolved problems in space engineering. Passive shielding, simply building thick walls, is counterproductive above a certain thickness because incoming cosmic rays interact with the shielding material and produce showers of secondary particles that can be more damaging than the original radiation. Active shielding, generating a magnetic field around the spacecraft strong enough to deflect charged particles, requires enormous power and superconducting magnets maintained at cryogenic temperatures. Sustaining such a system for years is challenging. Sustaining it for millions of years is inconceivable with any known technology. For a robotic probe, cosmic ray damage means progressive failure of electronic systems. Memory storage corrupts, processors malfunction, sensors degrade, redundant systems buy time, but redundancy is finite. Every backup eventually fails the same way the primary did. A probe crossing intergalactic space would undergo a slow death of its computational and sensory systems, losing capability year by year, century by century, until it was reduced to an inert mass of metal and silicon, drifting through the void with no ability to observe, record, navigate, or communicate. For a crewed vessel, the problem is orders of magnitude worse. The human body is exquisitely sensitive to ionizing radiation. Cosmic rays damage DNA, causing mutations that can lead to cancer, organ failure, and death. On the International Space Station, astronauts receive roughly 150 to 200 millisieverts per year, roughly equivalent to getting a full-body CT scan every 4 to 5 weeks. Their missions are limited to roughly 6 months to a year, in part because of this accumulated exposure. Long-duration missions to Mars would expose astronauts to significantly higher doses, a problem that remains one of the primary unsolved challenges for human deep space exploration. Between galaxies without the partial shielding of a galactic magnetic field, without the option of sheltering near a planet with a magnetosphere, and without the possibility of limiting exposure time because the journey itself takes millions of years, the radiation environment is not a health risk. It is a death sentence, not a quick one. A slow, generational degradation of the crew's genetic material, producing increasing rates of cancer, birth defects, and genetic disorders with every generation born aboard the ship. No known biological shielding eliminates this problem. The only defense is mass, enormous quantities of material between the crew and the outside radiation field, and the mass required to provide adequate shielding would make the spacecraft so heavy that the propulsion problem, already unsolvable, becomes even more extreme. And radiation is not the only biological enemy. A generation ship crossing intergalactic space would need to sustain a breeding population of humans for millions of years. The minimum viable population for long-term genetic health is debated, but most estimates place it in the hundreds to low thousands. A population that's small is vulnerable to genetic drift. The random loss of genetic diversity that occurs when a small group reproduces in isolation. Over hundreds of generations, genetic drift can reduce the health and adaptability of the population to the point where it can no longer sustain itself. Inbreeding depression becomes inevitable. Rare genetic disorders become common. The biological resilience that large populations maintain through sheer diversity is lost. Millions of years of isolated reproduction in a closed population would produce genetic effects that no human population has ever experienced. The crew would not just change culturally over that timescale, they would change biologically. Evolution does not stop because you are inside a spacecraft. Selective pressures in a ship environment, different gravity, different radiation exposure, different diets, different social structures would drive adaptation in directions impossible to predict. The people who arrived at Andromeda, if anyone arrived, might not be recognizably human by the biological standards of the people who launched the ship. This is not speculation about a distant possibility. It is the straightforward application of evolutionary biology to the timescales involved. 1 million years is enough time for significant speciation in many lineages. 25 million years is enough time for entire families of organisms to appear and diversify. The genus Homo has existed for roughly 2 to 3 million years. A ship traveling for 25 million years would carry its population through more than 10 times the total evolutionary history of every human species that has ever lived. And the biological changes are only one dimension of the transformation. The social and psychological changes would be equally radical, and they would begin far sooner. Human societies are not stable systems. They are dynamic, contentious, and fragile. Every civilization in recorded history has experienced internal conflict, factional division, ideological schism, and periodic collapse. Governments fall, religions fracture. Economic systems fail and are replaced. Social norms that seem permanent to one generation are incomprehensible to the next. The idea that a single governing structure could maintain coherent authority over a population confined to a spacecraft for millions of years is contradicted by every piece of evidence in the historical record. Within the first few centuries of a generation ship's journey, the original mission framework would face its first serious tests. The people born aboard the ship did not choose to be there. They inherited a journey that was imposed on them by ancestors they never met, toward a destination they will never see, for reasons that were formulated in a world they have no experience of. Some of them will accept this, others will not. Factions will form around competing visions of how life aboard the ship should be organized, what the mission's priorities should be, and whether the mission itself is worth continuing. This is not speculation. It is the predictable behavior of any human community under conditions of confinement, resource limitation, and generational succession. Studies of isolated communities on Earth, from island populations to remote outposts to submarine crews, show consistent patterns of social stress, hierarchy renegotiation, and conflict escalation under conditions far less extreme than permanent residence aboard a spacecraft with no possibility of departure. Within a few thousand years, the original language of the crew would have drifted into mutual unintelligibility with its earlier forms. The ship's records, written in the founding language, would require translation to be read. Within 10,000 years, the cultural continuity connecting the current population to the founders would be maintained, if at all, only through deliberate institutional effort, and institutions aboard a ship are subject to the same instabilities as institutions on Earth. A revolution, a religious transformation, a period of resource scarcity that forces a reorganization of social priorities. Any of these could sever the cultural thread connecting the present population to the mission's origins. Technical knowledge is equally vulnerable. Complex technological civilizations depend on an educational infrastructure that transmits specialized knowledge from one generation to the next. Engineers train new engineers, physicists teach physics, doctors pass on medical expertise. This chain of transmission is robust in large societies with redundant institutions, universities, libraries, professional networks, but fragile in small, isolated populations. If a generation ship's population drops below the threshold needed to sustain specialized training in all critical fields, knowledge begins to leak from the collective memory. A field that loses its last practitioner without training a successor is gone. The books may remain, but if no one alive understands them, they are decorative. Over tens of thousands of years, the loss of specialized knowledge could reduce a generation ship's population from technologically sophisticated crew members to people who live inside a machine they no longer fully understand. They would know how to operate certain systems through road procedure, the way a person can drive a car without understanding internal combustion. But the deeper understanding required to diagnose novel failures, adapt systems to changing conditions, or fabricate replacement components for technologies whose operating principles have been forgotten would be gone. The ship becomes a habitat rather than a vehicle. The population lives inside it the way organisms live inside an ecosystem, dependent on its continued functioning but increasingly unable to influence or repair it. The mission does not end. It transforms into something else entirely, a way of life disconnected from its original purpose, carried forward by inertia and habit rather than intention. And beneath all of these social and intellectual changes, there is a psychological dimension that is perhaps the most corrosive of all. A generation ship crew knows something that no human community has ever had to live with: the absolute certainty that they will never arrive. Not just that they personally will not see the destination, which is true for most generations aboard, but that no one they know, no one they will ever meet, no one alive within thousands of generations in either direction will see it either. The destination is so distant that it exists only as an abstraction, a number, a concept taught in classes and referenced in official documents, but never experienced as a reality that the living crew has any personal connection to. The psychological literature on isolation, confinement, and purposelessness suggests that this kind of existential disconnection would exact a severe toll. Depression, anomie, loss of motivation, and social withdrawal are documented responses to environments where individuals feel that their actions have no meaningful consequence. Aboard a generation ship crossing intergalactic space, the absence of meaningful consequence would be structural. Nothing the crew does will bring the destination closer in any time frame they or their descendants could perceive. The journey is a fact of existence, not a project with a foreseeable end. Living aboard the ship is not a means to an end. It simply is, a condition without resolution, stretching in every direction beyond the horizon of any individual life. Some thinkers have proposed that the crew would adapt, developing new cultural frameworks that find meaning in the journey itself rather than the destination. That is possible. Humans are remarkably creative at constructing meaning under adverse conditions. But the meaning they construct would bear no resemblance to the meaning the mission's founders intended. The mission would survive in name only. Its substance would have been replaced, generation by generation, with something entirely new. Something shaped by the realities of life aboard the ship, rather than the goals of the civilization that built it. Navigation adds another layer of impossibility. Inside a galaxy, navigation is complex but supported by an abundance of reference points. Stars are everywhere. Their positions are catalogued. Their motions are tracked. A spacecraft can determine its location and heading by comparing observed star positions against a known database, a technique called stellar navigation, which is a refined version of what ancient sailors did with the night sky. Pulsars, rapidly spinning neutron stars that emit regular beams of radio waves, serve as even more precise navigational beacons. Their signals are predictable enough that they function as natural clocks and position markers, and multiple space agencies have studied their use for deep space navigation. Between galaxies, the navigational landscape is barren. The stars of the home galaxy are behind you, receding into a single concentrated glow that offers no fine positional detail at great distances. The stars of the target galaxy are ahead, but from millions of light years away, they are not individually resolvable. The target galaxy appears as a diffuse patch, not a field of individual reference points. There are no pulsars to lock onto, no stellar catalogues to compare against, no dense star fields to triangulate within, and the target itself is moving. Andromeda approaches the Milky Way at roughly 110 kilometers per second, but it also has a transverse velocity, a sideways motion, that must be accounted for over the duration of the crossing. Over 25 million years, that transverse motion shifts the target's position by an amount that, while small in angular terms from the starting point, becomes significant as the spacecraft approaches and must make fine course corrections to arrive at a specific location within the galaxy rather than flying through an empty region of its halo. Course corrections require thrust. Thrust requires fuel. Fuel is finite. And the navigation system that calculates the corrections requires power, functional sensors, and operational computers, all of which are degrading under the assault of cosmic rays and the slow entropy of millions of years. Let us now consider the three categories of vehicle that could theoretically attempt the crossing, and examine what happens to each one. A robotic probe is the most plausible candidate. It does not need food, water, oxygen, or social interaction. It does not accumulate radiation damage in biological tissue. It does not evolve. It does not go insane from isolation. A well-designed probe, built from the most durable materials available and equipped with redundant systems, could theoretically survive longer than any crewed vessel in the intergalactic void. But a probe is still a physical object subject to the laws of thermodynamics. Its electronics degrade, its power source decays, its structural materials sublimate, are pitted by micrometeoroids, and are weakened by radiation damage. Even if the probe were built from the most radiation-resistant materials known, even if it carried 100 redundant copies of every critical system, the timescale of an intergalactic crossing would exhaust all of that redundancy. The probe would pass through a period of gradual failure, losing sensors, losing computational capacity, losing communication ability, losing navigational function, until it became a lump of matter traveling on its last known trajectory, with no ability to adjust, observe, or report. It would arrive at Andromeda not as a functioning probe, but as a relic a piece of engineered debris from a civilization that no longer exists, entering a galaxy that never knew it was coming. It would be the interstellar equivalent of a message in a bottle, except the bottle has been in the ocean so long that the glass has frosted over, the cork has rotted, the paper inside has dissolved, and nothing remains but a vaguely cylindrical shape tumbling in the current. A generation ship is the most ambitious crude concept. It envisions a vessel large enough to support a self-sustaining human population for the duration of the crossing, with closed-loop life support systems that recycle air, water, and waste, with agricultural systems that produce food, with medical facilities, schools, social structures, and governance systems that maintain order across an indefinite journey. For interstellar distances, generation ships are at the extreme edge of theoretical feasibility. A journey to Proxima Centauri at 1% of light speed would take roughly 425 years, perhaps 10 to 15 generations. That is an enormous social and engineering challenge, but it sits within the range of what long-duration planning can at least conceptualize. Human societies have maintained cultural continuity across 10 to 15 generations before. It is difficult, but not unprecedented. For intergalactic distances, the number of generations involved destroys the analogy. At 1% of light speed, the crossing to Andromeda takes 250 million years. That is roughly 10 million human generations. No social structure in human history has survived more than a few hundred generations. No governing institution has maintained continuous authority over the same population for more than a few thousand years. Even with abundant land, resources, and room to expand, a generation ship bound for Andromeda would need its internal society to hold together across roughly 1 million generations without external contact, without resupply, without immigration, and without any event horizon shorter than geological time. The problem is not whether the crew can be kept alive. The problem is whether 1 million consecutive societies, each inheriting the ship from the last, can be kept pointed at the same purpose. Nothing in the human record suggests they can. The ship's population would evolve, its culture would transform, its language would become unrecognizable, its understanding of its own origin would fade into mythology. Unlike the probe, the generation ship does not go dark. Its population continues to breathe, eat, argue, reproduce, and build meaning out of the only world they have ever known. Unlike the hypothetical advanced craft we are about to consider, it carries no technology capable of outrunning the social and biological transformations already described. It is the worst of both categories. Conscious enough to endure the crossing, but not capable enough to arrive as what it was when it left. And then there is the hypothetical advanced craft. The spacecraft built by a civilization far beyond our current capabilities, equipped with technology we cannot specify because it does not exist. Perhaps it uses some form of energy production we have not conceived. Perhaps its structural materials are engineered at the atomic level for maximum durability. Perhaps it solves the radiation problem, the navigation problem, and the propulsion problem through means we cannot anticipate. Even granting all of that, even imagining a craft built by a civilization 1 million years more advanced than ours, the fundamental constraints remain. The speed of light has not been repealed. The journey still takes millions of years at any subliminal speed. The crew, if there is one, still ages. The materials, however advanced, still interact with the radiation environment. Entropy still operates. Information still degrades. An advanced civilization might send a probe that survives the crossing in functional condition. That is within the realm of possibility, though it requires materials science and engineering far beyond anything currently imaginable. But even that probe arrives at a destination where its home civilization has aged by millions of years. It cannot report back in any operationally useful time frame. It cannot request updates. It cannot be repaired. It functions alone, forever, in a galaxy that did not build it, carrying instructions from a world that may no longer exist. The distinction that matters is the one between physical possibility and practical meaning. A spacecraft can, in principle, cross the void between galaxies. The physics allows it. There is no law of nature that prevents an object from traveling from the Milky Way to Andromeda. The distance is finite. The speed of light, while a hard limit, still permits subliminal crossing in a finite amount of time. But practical meaning requires more than physics. It requires that the journey serve a purpose that survives the crossing. It requires that the entity making the journey retain its identity, its function, and its connection to the reason it left. It requires that the arrival mean something to someone. At interstellar distances, that meaning is strained, but preserved. The journey is brutally long, but it ends within the span of a civilization's potential lifetime. The connection to home is thin, but real. At intergalactic distances, the meaning does not survive. The journey does not end within any recognizable frame of reference. The civilization that launched the mission is transformed beyond recognition or gone entirely. The crew, if biological, has evolved into something different. The probe, if mechanical, has degraded into something between a tool and a fossil. The purpose of the mission has been forgotten, rewritten, or rendered irrelevant by changes on both ends that no one could have predicted or prevented. The void between galaxies does not destroy spacecraft through dramatic violence. It does not crush them, burn them, or tear them apart. It does something quieter and more absolute. It outlasts them. It simply takes longer to cross than anything human, or anything built by humans, can remain intact and functional. And what that means for the way we should think about galaxies, those bright spirals and glowing ellipses that decorate every astronomy textbook, is the final piece of this story. Because galaxies are not simply far away, they are a different kind of far. A kind that does not just test our engineering, it tests whether the word journey still means what we think it means. There is a particular cruelty in something you can see, but cannot touch. A glass of water behind a locked door when you are dying of thirst. A shore visible from a raft that the current carries in the opposite direction. The cruelty is not in the absence of the thing. It is in its presence. You know it exists. You can describe it in detail. You can watch the light reflect off its surface, and none of that brings it any closer. Galaxies are the largest version of this cruelty that the universe has ever produced. On a dark night, the Andromeda Galaxy is visible to the naked eye. You can see it. A faint smudge of light, wider than the full moon in apparent size, sitting quietly in the constellation that shares its name. Binoculars reveal its elongated shape. A modest telescope shows the bright nucleus and the faint suggestion of a spiral structure. Professional instruments resolve individual stars, map the distribution of gas and dust, measure the chemistry of its stellar populations, track the motions of its satellite galaxies, and reconstruct its history across billions of years. We know Andromeda with extraordinary intimacy. We know its mass, roughly 1.5 trillion solar masses. We know its diameter, more than 150,000 light years. We know it contains approximately 1 trillion stars. We know the types of stars it has, the regions where new ones are forming, and the ancient globular clusters that orbit its halo like remnants of a younger era. We know all of this because light is generous. It leaves Andromeda freely, crossing the intergalactic void at 300,000 kilometers per second, requiring nothing, consuming nothing, carrying information encoded in its wavelengths and arrival times that telescopes can decode with astonishing precision. Light does not need fuel or shielding. It does not need to remember why it left. It does not degrade over distance in any way a larger receiver cannot compensate for. It simply travels, arriving 2.5 million years later with a portrait of the galaxy it departed from, old by human standards, but pristine by the standards of physics. This is why galaxies feel close. We see them constantly. They appear in every deep field image, every wide survey photograph, every astronomy textbook. They are among the most photographed objects in existence. Their shapes are icons, spirals, ellipticals, irregulars, barred spirals, ring galaxies, interacting pairs trailing streams of stars between them. They are beautiful. They are familiar. And that familiarity creates a psychological proximity that has no basis in physical reality. Because light can cross the void between galaxies, but nothing else we know of can cross it and retain its meaning on the other side. This is the central asymmetry of intergalactic distance. Information flows freely. Matter does not. Photons cross the gap between galaxies as though the gap does not exist, carrying detailed reports about conditions on the other side. But a spacecraft attempting the same crossing would face every problem described throughout this story. Power failure, material degradation, radiation damage, navigational blindness, communication severance, and a journey duration that outlasts civilizations, species, and possibly the structural integrity of the vehicle itself. We live in a universe where we can study what we cannot visit, where we can know a place in extraordinary detail and never set foot there, where the information about a destination arrives perfectly, but the means to reach the destination do not exist and may never exist. And the universe is not finished making this problem worse. Within the local group, the roughly 50 galaxies gravitationally bound to each other, the distances are large but fixed. Andromeda is 2.5 million light years away and getting closer. The Magellanic Clouds orbit within a few 100,000 light years. The Triangulum Galaxy sits at roughly 2.7 million light years. These distances will change over cosmic time as the galaxies interact, merge, and reorganize. But they will not grow. The local group is a bound system. Gravity holds it together. The galaxies within it are, in a sense, permanent neighbors. Impossibly distant neighbors, separated by voids that no human mission could survive crossing, but neighbors nonetheless. Beyond the local group, the situation is different. The universe is expanding. Space itself is stretching, carrying galaxies apart from one another at rates proportional to their separation. Within the local group, gravity overwhelms this expansion. The galaxies are close enough and massive enough that their mutual attraction keeps them bound. But beyond the local group's gravitational reach, cosmic expansion dominates. The Virgo cluster, the nearest large galaxy cluster, sits roughly 54 million light years away, and it is receding from us. The galaxies beyond Virgo are receding faster. The further you look, the faster the recession. This expansion is not galaxies moving through space. It is space itself growing, new distance being created between objects that are not gravitationally bound to each other. And the rate of this expansion is accelerating, driven by a force called dark energy that constitutes roughly 68% of the total energy content of the universe, and whose nature remains one of the deepest unsolved problems in physics. The acceleration of cosmic expansion means that galaxies beyond a certain distance are not just far away. They are getting farther away faster than light can cross the growing gap between us. This sounds like it should violate the rule that nothing travels faster than light, but it does not, because the galaxies themselves are not moving through space faster than light. Space is expanding between them. The distinction is subtle but physical, and its consequence is absolute. There exists a boundary called the cosmological event horizon, beyond which no signal, no spacecraft, no photon emitted today will ever reach us, no matter how long we wait. Galaxies beyond that horizon are not merely far, they are permanently and irrevocably cut off. They will never be observable again. They will never be reachable. They will fade from the observable universe as their light is redshifted into wavelengths too long to detect, and eventually they will vanish entirely from any instrument we could conceivably build. This process is already underway. The observable universe contains roughly 2 trillion galaxies. The vast majority are already receding at velocities that will eventually carry them beyond the event horizon. Over the coming tens of billions of years, the night sky will empty. Galaxy clusters outside the local group will be carried beyond the horizon one by one, their light stretched into invisibility, their existence erased from any conceivable observation. In the far future, the only galaxies remaining in the observable universe will be the members of the local group, by then likely merged into a single large elliptical galaxy. A civilization living in that era, looking out at the sky, would see nothing beyond its own galaxy, no other galaxies, no evidence of cosmic expansion, no Hubble tension, no dark energy, no large-scale structure. The universe would appear to contain a single island of stars floating in an infinite empty void, and there would be no observational evidence to suggest it had ever been otherwise. The information about the rest of the universe, the 2 trillion galaxies, the cosmic web, the evidence of the Big Bang written in the microwave background, all of it will have been carried beyond the horizon by the same expansion that once made it visible. A civilization in that era would have no way to discover the full history of the cosmos. The universe would have hidden its own past. This is the largest scale expression of the same cruelty that defines intergalactic distance at every level. The universe shows you things and then takes them away. It lets you observe galaxies you cannot reach. It lets you study cosmic history you will eventually be unable to access. It gives you light as a window and then slowly closes the window by stretching space until the light can no longer arrive. But that is the far future. The nearer and more immediate version of this cruelty is the one that applies right now to the galaxies we can already see, the ones that appear close enough to study in detail, close enough to photograph in color, close enough to feel like they are a part of our neighborhood. Andromeda is the sharpest example. We know it better than almost any galaxy outside our own. We have mapped its dust lanes. We have catalogued its globular clusters. We have measured the rotation curve of its disk and used it to infer the distribution of dark matter in its halo. We have identified its satellite galaxies, M32 and NGC 205 and track their interactions with the larger structure. We have studied the streams of stars being pulled from dwarf galaxies as they are consumed by Andromeda's gravity. And the Milky Way and Andromeda are connected, at least gravitationally. Their dark matter halos already overlap, extending far beyond the visible boundaries of each galaxy and merging in the intergalactic space between them. The two galaxies are part of a single gravitational system, falling toward each other at the speed established earlier in this story, locked in an interaction that began billions of years ago and will play out over billions more, requiring no fuel, no maintenance, and no conscious decision at any point along the way. Whether they will fully merge is, as of 2026, genuinely uncertain. The competing studies described earlier in this story disagree by a wide margin, with merger probabilities ranging from roughly 50% to 90% depending on how the gravitational influence of the local group's other members is modeled. The data is still being refined. The transverse velocity of Andromeda, the single measurement that matters most, remains difficult to pin down with sufficient precision. But the outcome of that debate does not change the point that matters here. But whichever outcome occurs, one detail remains the same. If the merger happens, it will happen through gravity. The two galaxies will fall toward each other across 2.5 million light-years of void, their mutual attraction pulling them together across a timescale of billions of years. No engine will drive them. No navigation system will guide them. No crew will monitor the approach. Gravity will do what no spacecraft can: cross the intergalactic void without power, without fuel, without maintenance, without a deadline. It has the one advantage that changes everything. It is patient beyond any scale that engineering or biology can match. And even gravity takes billions of years to close a gap of 2.5 million light-years. That is how large the distance is. The most powerful force shaping the large-scale structure of the universe, operating without interruption for longer than the Earth has existed, still requires billions of years to pull two neighboring galaxies together. A spacecraft trying to cross the same gap on purpose, carrying living passengers or functioning instruments, is attempting to do by engineering what gravity does by geometry. And it is attempting to do it on a timescale where every component of the spacecraft, from the hull to the fuel to the population to the mission itself, will have crumbled, evolved, forgotten, or expired long before arrival. This is where the meaning of the word dangerous becomes precise. The distance between galaxies is not dangerous the way a black hole is dangerous, or the way a supernova is dangerous, or the way radiation during a solar storm is dangerous. Those are acute hazards. They threaten to destroy a spacecraft, or kill a crew in moments or hours or days. They are violent. They are dramatic. They can be studied, modeled, and in some cases defended against. The distance between galaxies is dangerous in a different way. It is dangerous because it is patient. It does not destroy in a single event. It dissolves across duration. It takes every problem that already makes interstellar travel extraordinarily difficult and stretches each one into a timescale where solutions stop working. Not because the solutions are wrong, but because nothing survives long enough to apply them. Power systems decay, materials erode, electronics fail, biological populations evolve beyond recognition, cultures transform, languages die, mission purposes are forgotten, home civilizations change into something unrecognizable or disappear entirely. Communication, already impractical at interstellar distances, becomes ceremonial, a transmission of data into a future that has lost the ability to interpret it. Rescue becomes a concept without a referent, a word that describes an action no one can perform within a time frame that matters. Return becomes incoherent, a journey back to a place that no longer exists in any form that the word home could honestly describe. None of these failures is violent, none is sudden. Each one is the quiet, predictable result of time applied to physical systems in quantities that no human institution, no biological organism, and no engineered object has ever been designed to withstand. And this is what separates intergalactic distance from interstellar distance in a way that most descriptions fail to convey. Interstellar distance is a barrier. It is enormous, it is daunting, and it may be practically insurmountable for human crews with any technology foreseeable in the next several centuries. But it is a barrier of degree. The problems it creates are extreme versions of problems we already understand. A faster engine, a better shield, a more resilient life support system, each of these pushes the boundary outward. The distance to the nearest star is a wall, but it is a wall that, in principle, engineering might one day climb over. Intergalactic distance is not a higher wall. It is a wall of a different substance. The problems it creates are not extreme versions of interstellar problems. They are transformations of those problems into challenges that exist on a time scale where the concept of solving them loses coherence. You cannot engineer your way across a gap that takes longer to cross than your species has existed. You cannot maintain a mission across a duration that exceeds the lifespan of every civilization, language, and political system in human history by a factor of thousands. The problem is not that we lack the technology. The problem is that the technology would need to outlast time itself, and nothing does. This is the thought that should sit with anyone who looks up at the Andromeda galaxy on a clear night and feels a sense of wonder. That smudge of light is real. The trillion stars it contains are real. The planets orbiting those stars, the chemistry happening on those surfaces, the physical processes unfolding across that immense rotating disk, all of it is real. And it is visible. Right there in the sky, observable with nothing more than a functioning human eye. And it is unreachable. Not because some force prevents the crossing, not because a barrier blocks the way, not because the laws of physics forbid the attempt, but because the distance between here and there is so vast that any crossing would take longer than anything human can endure. Longer than a crew can survive. Longer than a machine can function. Longer than a purpose can be remembered. Longer than a civilization can hold itself together. Longer than a species can remain what it was when it started. The Milky Way is not alone in the universe. We can prove that every time we point a telescope at the sky, galaxies surround us in every direction, billions of them, stretching to the edge of the observable universe. Each one is an island of stars, a gravitational system holding together hundreds of billions of suns, with planets and moons and all the raw ingredients that physics and chemistry need to produce complexity. The universe is not empty. It is crowded with structure, with light, with potential. But each island is separated from the next by a moat that is not made of water or fire or any substance that can be crossed with sufficient courage. The moat is made of time. It is made of millions of years of travel through a void where nothing can be repaired, nothing can be resupplied, nothing can be rescued, and nothing can remain what was a departure. Galaxies are not destinations separated by empty space. They are islands, separated by duration. And the duration is so immense that crossing it does not feel like travel. It feels like erasure. The person who leaves is gone, not dead in the way a person is dead when their heart stops. Gone in a deeper sense, erased by the passage of so much time that their origin, their context, their language, their species, and their world have all moved on without them. They are not exploring. They are disappearing. And the place they left behind is disappearing from them at the same rate, receding into a past so deep that it becomes inaccessible, indistinguishable from myth, indistinguishable from nothing. This is the truth that intergalactic distance forces us to confront. Not that the universe is big. Everyone knows the universe is big. Not that travel is hard. Everyone understands that space is difficult, but that the universe can show us things it will not let us have. That it can fill the sky with light from 1 trillion stars and place those stars behind a distance where help vanishes, return dissolves, and the journey itself becomes indistinguishable from disappearance. The Milky Way sits in its corner of the local group. Andromeda hangs in the sky, visible, studied, mapped. The light between them flows freely, carrying information in both directions at the fastest speed the universe allows. And that light is all that will ever cross the gap in any meaningful way. It arrives here carrying a portrait of a galaxy we will never visit, painted in wavelengths we can decode but distances we cannot survive. Between galaxies, the universe is not hostile. It is not dramatic. It is not filled with obvious threats or cinematic dangers. It is simply too large. And in that vastness, every system that humans depend on for travel, for communication, for rescue, for return, for continuity, for meaning, breaks down. Not through violence, through patience. The void does not attack. It waits. And it waits longer than anything built by hands or born of cells can hold together. You can look at Andromeda tonight. You can see it with your own eyes. It is right there. 2.5 million light years of nothing between you and 1 trillion stars. The light will keep coming. The photographs will keep getting sharper. The data will keep revealing new details about a galaxy that is, in every scientific sense, well understood. And it will remain exactly where it is. Visible, beautiful, studied, unreachable. The distance between galaxies is not a number. It is a sentence. And the sentence says, you can see everything the universe has built, but you cannot cross the space between the things it has built, because that space is not empty. It is filled with time. And time, given enough of it, erases everything that tries to cross.